We have covered the first item and talked about what method is used in science, and I think we have arrived at the next slide, which is about subject-object duality. Now, this is a concept in philosophy, and it's quite important in science, in the practice of science. And let's see what this means. Newtonian science is founded on the possibility of objective knowledge, as we have discussed. The world is something that we can know. The world is knowable, according to the scientific paradigm of Newton. And it is also knowable objectively. Objective knowledge is possible because it is objective, because it is obtained through independent observation. Actually, this idea is also formulated as subject-object dualism. Now, what we mean by the subject and the object is that subject is the active agency or party, and the object is the passive agency or the party. What happens is that whoever is the subject makes an observation on the object, okay? And by duality, we mean that it is possible to separate the observer from the observed. The observer and the observed can be separated from each other in the sense that the observation is made independently of the observed. Putting it in other words, we mean by this that the observer or the subject, by making an observation, does not produce any difference in what is observed. In other words, the observation does not affect the object, the observed. They can be separated. This is the idea of subject-object duality or dualism. It says that the observer, that is the subject, can be separated from the observed, the object. That is, if the observer makes observation independently of the observed, then observation will be objective. Is this clear? Sometimes it is possible that and we shall see examples of this in a few minutes, sometimes it is possible that making an observation produces a change in what we are observing. If we believe in the duality, it means that this will not happen. Making an observation will not produce any changes in what we are observing, okay? This is the idea of separation. Now, positivism is something you have all heard about. For example, we talk about positive sciences, and in Turkish, müsbet ilimler is something which has a high esteem in our perceptions. We think that positivism is good, okay? It is somehow associated with science. Science is supposed to be positive. Now, this idea of positivism is one school of thinking, actually, and we shall see others later on. But briefly, as we understand positivism from our everyday experiences or from our previous experiences, it is strongly rooted in this assumption. That is, if I ask you to define positivism, of course you can give quite a few different, similar but different definitions, but a good definition is that positivism is the belief that science can be conducted by separating the subject from the object. The fundamental assumption of positivism is this subject-object duality. So it is strongly rooted in this assumption. It claims that scientific inquiry can be objective. Why can it be objective? Because the subject can be separated from the object. By objective, we mean that it is strictly free of personal preferences and value judgments, and therefore able to provide true knowledge. Why is it strictly free of whose personal preferences would be important here? The subjects. The subject's personal preferences could could contaminate or could distort truth or reality. But since the subject is separated from the real world, in a way, the object is the real world, there will be no possibility of this sort of personal preferences and value judgments of the observer distorting the observed. Well, this was very nice, and it worked quite a long time, at least 150, 200 years after Newton. I mean, these ideas of objective science, the possibility of objective science and the knowability of the possibility of knowing the world worked very well. It worked very well because of the success of science. Science has shown great successes and advances since the time of Newton, as you know, until about the 20th century. About the beginning of the 20th century, things started to change. This belief in science, this confidence that science would take us to true knowledge, started to be questionable because of several developments. Some of these are written here, but when we come to lecture 4 on complexity, the notes that I shall post on the website will detail these, we'll have greater details about these developments. Let's see now briefly what these are. The first thing that happened, which shook the credibility of Newtonian science, happened in physics. In physics, the most important discoveries and theories of physics in the 20th century have been the theory of relativity proposed by Einstein in 1905 and quantum theory, which again Einstein contributed to and formulated in the beginning, but later on was developed by other physicists. Now, quantum theory is very, very important. It looks at physics at a very, very low level. We talked about levels. We talk about it again, but levels of observation. If you observe something from very high, you can't see everything. But if you come down to the level of, for example, molecules, or even if you go below that to the level of atoms and atomic particles, etc., you see things in much detail, and that's what quantum mechanics does. It studies subatomic particles, and what was discovered in quantum mechanics is that these subatomic particles do not exist as independent things. They come into being and are observed only in relationship to something else. Some of you will know what's this principle. What's the principle involved in this statement? There's a very famous principle, which is yes, Heisenberg's, the physicist Heisenberg, who received the Nobel Prize, I think in 1931 or something like that, when he was very young, he formulated and he proved a theorem which is known now as Heisenberg's uncertainty principle. They were trying to, the electron was discovered by that time, and they were trying to, physicists were trying to assess or measure, let's say, the speed and the mass of the electron. Particles have two such attributes, speed and mass. And it was discovered that if you try very hard to measure the velocity of the electron, the speed of the electron, the mass changed in a way. And if you, on the other hand, if you tried to measure the mass accurately, you couldn't measure the speed. So the speed and the mass could not be at the same time. It could not be determined. This is called Heisenberg's uncertainty principle. Why does this happen? Because when you are observing the speed, you are making an effect on the mass and vice versa. So observation influences the observed. So subject-object duality was seen to fail in physics, in reality. So you cannot separate actually the subject from the object. So this was a very, very powerful result which shook our confidence in positivism and in the objectivity of science. Similarly, there were many other developments in all disciplines of science. Biology is very important. In biology, it was understood that organisms are adaptive. We now know what we mean by adaptive. What does it mean, adaptive? You know, we reviewed concepts of data, information, knowledge, etc. And also we reviewed concepts of knowing, understanding, learning. What was learning about? Learning is associated with feedback, adaptation is learning under changing conditions. So adaptive means that the environment affects knowledge. Adaptive signifies that. And organisms, therefore, they learn and they obtain knowledge and they behave according to conditions that are imposed on them by the environment. And it is completely different from the understanding of Newtonian mechanics. Okay? Co-evolutionary. Organisms are co-evolutionary, means they evolve within their habitat together with the ecosystem. So that was also something new. And this last item, which is more difficult to understand, and maybe we shall spend some time on it later on, is very, very important. In chemistry, disorder in dissipative system. A dissipative system is a system idea which attribute which is related to the theorems of thermodynamics, the second law of thermodynamics, which is extremely important in not only in chemistry or in science, but it is also important in social sciences and in human practice, this idea of the second law. Probably you are aware of the second law of thermodynamics. You have taken the thermodynamics course, right? Well, probably you heard about this theorem. A dissipative system, actually, this is about entropy, the concept of entropy. I shall spend some time on this in lecture 4, so this is just a preliminary remark. But the concept of entropy, I assume that you are familiar with this concept, is, for example, you know that energy can neither be created nor destroyed. So the amount of energy, however you measure it, is supposed to be constant. And it is constant as far as we know today. It is constant, but this energy also, as you know, is dissipated. It is used up. For example, we are using up energy obtained from fossil fuels for hundreds of years now, at least 200-300 of years, or even before, because we have been burning wood, for example. Wood is not fossilized fuel, but when wood becomes fossilized and other organisms become fossilized, they turn into oil and coal. And we are dissipating the energy embedded in these resources. And where is this energy going? So you see, energy comes in two types, actually. One type of energy is the one that you can use, and since the total energy is constant, something must be happening. We are reducing the amount of usable energy, but there must be the unusable, let's say. I'm talking in everyday language, not in scientific terms now, must be increasing. This increasing non-usable energy, in a way, is called entropy, right? So dissipative systems, actually life itself is a sort of a dissipative system. In the end, according to the second law, what will happen in the end? In the end, at time infinity, whenever that arrives, all usable energy will be dissipated, and the universe will look like a soup, chorba. And that's called thermodynamic equilibrium, when everything will die, the universe will die. That's what the second law tells us. So the chemist Prigogine, actually, who received the Nobel Prize in 1977, I guess, made very powerful contributions to this theory. And it was discovered in this that these dissipative systems, which are constantly losing, fighting against entropy, but this fight is hopeless in the limit because entropy cannot decrease. Entropy is always increasing. Is that growth is found in disequilibrium, not in equilibrium. Now, the idea here is, that is why this is relevant for us, is because Newtonian science is founded on physics, ideas from physics, which are equilibrium, stability, momentum, etc., laws of motion. You are all familiar with this from your physics courses. But here we see that the fundamental state in nature is not equilibrium but disequilibrium because of dissipation. Okay, so these are ideas which which run contrary to the Newtonian paradigm. You see, when the universe reaches thermodynamic equilibrium, all universe will be disordered. Entropy is disorder. Energy, the usable energy, provides order. Okay? Life, for example, started with the cell, the single cell on Earth. What's the most important property of a cell, do you think? As I said before, that it has a cell wall. There's a boundary of the cell. The cell must differentiate itself from the environment in order to exist. Okay, life starts like this. So how can the cell differentiate itself from its environment and continue to exist? By importing energy from the environment. It has to import energy. It has to use this energy. So energy provides order. In disorder, you don't have anything different from anything else. That's why we said that the universe will look like a soup. Çorbaya benzeyecek. A soup is just something which has no differentiation. Okay? But this is a living organism. It is organized, means it is ordered. Organization in this illustration is used in the sense of order. Okay, so this new awareness led to the movement of systems, as we said, and it emphasized relationships that exist among parts which look independent of each other, but in fact which are not. When we view the world from this systems perspective, we enter an entirely new landscape of connections, of phenomena that cannot be reduced to simple cause and effect, and of the constant flux of dynamic processes. So this is another quotation from the same reference. It means that in systems, the observer inevitably influences the observed. Maybe I should have underlined this. The observer inevitably, it's inevitable that you have to influence the observed, since he must be part of the system. Since they are in the same system, and since the parts of the system interact with each other, influence each other, subject-object duality is not possible, actually. And at the same time, or because that subject-object duality is not possible, absolute objectivity also is impossible, is not possible. So these are new realizations and understandings. For example, you have conducted some experiments in the physics laboratory, I believe, or in the chemistry laboratory when you are taking courses. In the laboratory, when you are conducting an experiment, you make observations. Do you think the subject-object duality holds in a laboratory like a physics laboratory? You are conducting a chemical experiment, for example. You are mixing some ingredients together and trying to see what happens as a result of that. Or maybe you are, for example, swinging a pendulum in the physics laboratory and trying to measure the amplitude of swing, etc., or its speed. Do you think that the subject-object duality is intact, holds in a physics laboratory? Well, the answer is, I think it is difficult to say that in a physics laboratory the subject-object duality fails. It doesn't really fail. But ultimately, if we force our argument a little bit, it fails. Why does it fail in a physics laboratory? How does the observer influences what is observed? I mean, the pendulum is swinging. It's a laboratory, so there's no air currents, which may affect the speed of the pendulum. The observer does not touch it, etc., etc. So they must be separated. But why would the duality fail? Why should I be able to say that the duality does not hold even in a physics laboratory? Well, you see, the idea is the observer is observing the pendulum. So he has made a decision. He has made a choice. He has made the choice of observing the pendulum and not something else. Do you understand this? The scientist cannot be free of personal judgments. What is the agenda of the scientist? To conduct experiment A. But there's also the possibility of conducting experiment B. But I have chosen to conduct experiment A, so I have made a judgment. Do you understand this? Therefore, complete and absolute objectivity is not possible. Why are you observing this phenomena and not that phenomena? So you must have made a choice. So the choices of the scientist will ultimately, in the end, have an effect on what is being observed. Okay? So this is the idea of systems, actually. That subject-to-object duality in absolute terms cannot hold. Furthermore, what was observed in the 20th century was that most of the systems that we are trying to understand have the property of complexity. Now, this idea is at least as important as the idea of systems. And as we shall see in the next lecture, complexity theory coincides in most parts with systems thinking. So they appear to be the same thing, as we shall see later on. But they developed not all together, but in different courses again, as we shall see. So complexity is also something that we realized in the 20th century. The idea, for example, didn't Newton know about complexity? Well, he was also aware of complexity. There's the famous problem in physics called the three-body problem. The three-body problem. Newton was able to solve the two-body problem. Actually, an example of the two-body problem is to compute the path that the Earth traverses around the Sun, for example, or the Moon around the Earth. When the Moon revolves around the Earth, you can compute the path. Mathematically, it comes out as an ellipse. There are some examples of this in calculus, if you remember. So Newton was able to compute that part. And, and since the formulas, the solution was available, you could, for example, determine the exact location of one body, of the two bodies, sometime in the future by using the solution. Newton also tried to compute the equations, the solution, the motion, the equations of motion for three bodies. For example, the Earth, the Moon, and also the Sun all together, and was not able to solve that. But he thought that, well, in the future somebody might solve it. And after Newton, maybe for, when did Newton die? I think for close to 200 years, mathematicians tried to solve the three-body problem. But what happened in the end is, I think in 1905 or something, Poincaré, the French mathematician, proved that it wouldn't be possible to solve that problem. So you see, the three-body problem was a problem of complexity, complex problem. Newton didn't know that, didn't realize that. He thought that his science, or the Newtonian or the modern science, would be capable of solving all these problems and arriving at knowledge, true knowledge. But Poincaré proved that the three-body problem did not have a closed-form solution. Of course, by computer approximations, people could compute the location of the three bodies from time 0 into some time t, for example. But an analytical solution was not available. It's because the three-body is, with the force of gravity, attract each other in a complex way. And the idea is that if we have complexity, then the knowability assumption is shaken. We were assuming that the universe, the nature was, the world was knowable since Newton. Complexity tells us that, well, it's not as easy as that. It may be impossible to know the world. This is the idea of complexity. Now, complexity theory is, as I said, is probably the most important agenda of science in the 21st century. And we shall talk about it in greater detail in the future. But as far as it concerns us here, let's make some comments. Despite all these developments in biology, in quantum mechanics, etc., the positivism still persists in science. It's not dead. The positivist, objectivist, disciplinary approach is still used, and some scientists strongly still believe in positivism, at least not in the absolute sense, perhaps, but the idea of positivism is not easy to leave behind. By contrast, operational research has had an interdisciplinary character from the start and became aware early on of the impossibility of value-free inquiry. Now, operational research, as you know, started in the 1930s, before the Second World War in Britain. And the problems that they were dealing with, starting with the deployment of the radar against German attacks, etc., were attacked. I mean, the problems were addressed by teams of scientists and engineers from different areas. So interdisciplinarity of OR was, known and understood much before interdisciplinarity has been appreciated in science, much before then. And also OR knew that inquiry could not be value-free. The observer and the observed cannot be separated. The nature of OR makes this very clear from the beginning. Today, even everyday decision-making faces complexity. Now we are moving to complexity. For example, the impossibility of value-free inquiry is a factor which increases complexity, as you can understand. Today's world has thus increased in complexity and interdependence to a point where the traditional methods of problem solving based on the cause and effect model cannot work, cannot cope any longer. Now, let's see some examples from our textbook, which illustrates the complexity of the problems that industrial engineers are likely to be involved in. These problems are simple examples, and they illustrate complexity by underlining unexpected and undesirable consequences when you try to solve a problem there without regard to systems thinking. If you try to solve a problem moving from the Newtonian perspective and not from the systems perspective, you are likely to face unexpected results. Some of these unexpected results could be positive, but some could also be negative, undesirable. So 3 examples are given in our textbook. The first one is the Aswan Dam in Egypt. Now, you know the River Nile is a very long and powerful river. This river is very important for the economy of Egypt. The floods, it floods every year. It floods, and when it floods, a lot of most of the shores are underwater, and then the waters recede, etc. And this leaves very fertile soil where the Egyptians do their farming. They have been farming the shores of Nile for maybe 5,000–6,000 years, as you know, since the beginning of written history. And in the 1950s, the Egyptians, the Egyptian President Nasser, who kicked out the Egyptian king by a military coup, Colonel Nasser became president, and he decided to improve the economy of Egypt and the livelihood of Egyptian farmers by building a very large dam on the Nile. And in Aswan, this is some hundreds of kilometers to the south of the Mediterranean. This was a very famous dam. I was a child when the dam was being built, and it was news in the newspapers. They said that the height of the dam reached so many meters, etc. It was a politically sensitive project because the Americans and the West did not give any money, any credit to Nasser for building this dam, and he went to the Soviet Union, and then he founded the Socialist Republic of Arab Socialist Republic, etc., where Syria and Egypt became one nation for some years. So this was a very famous project. The idea was, of course, to increase the crop, the agricultural produce, by controlling the flooding according to the needs of farming, of agriculture. But what happened is that most of the silt is what remains when the waters recede. The waters carry a lot of topsoil from upriver, and then after the flooding, of course, this very valuable and agriculturally fertile soil, which is called silt, is left, and this helps the farms a lot. But when you put a dam, the power of the floods will decrease, and the accumulation of silt will not be as before. So fertile silt was lost when the dam was built. But the idea of the dam was, of course, to improve agricultural conditions. Something unexpected like this occurred, and they had to start using fertilizers, suni gübre. Before the dam, there was no need to use any fertilizers. Also, salinization. Salinization means, of course, the increase in soil of the quantity of salt. When salt accumulates, again, this is very bad for agriculture. there were sardine fisheries at the mouth of the Nile. A lot of sardine fisheries were operating there, and they lost most of the land on where they were doing this fishery, where they had their fisheries. A disease called schistosomiasis. This is a very important disease that people working in wetlands in the water, they take this disease from some parasites living in the water. This increased a lot. So the Aswan High Dam, when you decide to construct such a dam with the expectation that it will help with your agriculture, then since it's a complex, because a dam changes the ecology, and ecology is probably the most complex system that we can, one of the most complex systems around. So these unexpected and all of these are negative results can occur. Another example is about urban transport. Now, in Turkey, in big cities of Turkey, you know that population is always increasing. And when population increases, the city starts to extend through its circumference, and the areas, the new areas, are called suburbs. Suburbs. For example, I live in Çayolu. Çayolu is a suburb of Ankara. It will maybe very soon become the center of Ankara if Ankara keeps growing like this. But suburbanization, this increases car ownership. If you live 20 kilometers from the center of the city, people would tend to buy automobiles, and car ownership increases like that. This also makes it necessary to extend the road network. And you can see that around Ankara always new roads are being constructed. What happens as a result is that the demand for public transport is reduced by increased car ownership. I mean, this may not exactly apply to the example of Ankara, but you can imagine such a situation. When the demand for public transport decreases or is reduced, the costs, the unit costs of public transportation will go up because of diseconomies of scale, probably, and fares. The fares are the money that you pay for a ticket. They will go up, and service quality may decline because there is less demand for public transport. So what happens is that this provides further cause for the increase of private transportation, and that creates traffic congestion. You see, if in the beginning, for example, we were suffering from bad traffic in the town, we start to build suburbs and divert people to reside from the, instead of living in the center of the city, let them go elsewhere so that there will be less traffic in the city. But what happens as a result of these chains of events? Traffic now becomes even more congested than before. So this has happened in almost all cities over the world. It's again a measure of complexity that leads us into thinking that we can solve the problem by constructing new roads and suburbs, etc. The problem does not go away. It comes back in greater force. This is just another hypothetical and easy example. When you start industrial engineering courses in our department, we usually put this sort of situation. Let's say, for example, that we have a production system, and we would like to minimize the costs, the total costs of the production system. Cost minimization is associated with efficiency, as you know. So if there are, for example, 4 stations in the production system, we can try to optimize the performance or the efficiency of each single station. When we optimize each workstation, the system, overall system, is expected to be optimized as well. So this is the idea. So these are machine centers, okay? Assessing the performance of each machine center on the basis of average unit costs. If the average unit costs are minimized at each machine center, the performance of each machine center is optimal. The lower the unit cost, the more efficient the machine center. This assessment works fine in simple plants. For example, if you have a single machine center, then this will work fine. If you optimize it, the system will have been optimized. But in a complex setup with several centers working together, it can lead to accumulation of work in process inventory, profit loss, etc., etc. So these are ideas that are familiar to us. So the obvious solution often makes things worse. You try to remove the insects from your plants, but then you kill your chickens as well if you are not very careful. Here is a numerical example provided in the textbook. It's very simple, but it's nice. Suppose that we use two raw materials, A and B, in a production facility and turn them into finished products, A and B, as you can see. The raw materials for product A cost 50 pounds per unit. And then, of course, the production itself, there are labor costs. The labor costs, we have a production capacity of 8 hours per day. And each hour of labor costs 20 pounds. Product A needs 2 hours per unit. These are the requirements. And product B needs 1 hour per unit. So the total costs of the products are both, as you can see, 90. 50 plus 2 times 40 is 90. And 70, product B, the raw material costs 70 pounds. 1 hour of labor costs 20. 70 plus 20 is again 90. So for both products, the total costs are 90. But the selling prices are different. Product A can be sold at 180 pounds. It's more expensive than product B, which can be sold at 150 pounds. So the margin, the profit margin, is in product A, it is how much? 90 pounds out of 180 pounds of price. 90 pounds is your profit. And for product B, the profit, the margin, is only 60 pounds. So you might, for example, say that, let me produce, and there's a demand for these products. You can sell 3 units of A and 4 units of B in a day. So given this data, this is a simple optimization problem, but let's assume that we try to solve this problem by producing as much as possible of the more profitable product. What is the more profitable product? It's product A. So the solution on the left is the result of this. Produce more of the high margin. Margin means profit. Margin in management language, margin and spread both mean profit. So then you have, when you maximize the number of the high margin item, you can produce 3 units of that and 2 units of the low margin item, and you get a profit of 390. But if you maximize the number of the low margin item instead of the high margin item, your profit will be 420. So you see, this is again something not intuitive if you don't solve this systemically. But of course, we know that this is an optimization problem. We look at we evaluate all the data and for example, formulate an LP problem here, and we shall be able to get the correct solution. But if you are stupid and if you do not look at the whole system and just try to maximize the number of the most profitable item as much as possible, then you end up with a suboptimal solution. So this is just a good example, a counterintuitive production example. There's another example mentioned in our textbook. It's about the Hawthorne effect, which is very, very famous. Probably you are already familiar with this effect. Yeah, you have met this before. The idea is that Hawthorne is a town in the United States where they conducted experiments about productivity and tried to see whether illumination is better. When the illumination, the lighting is better, productivity would increase. An experiment designed with an experimental and a control group. Now, these are important in science. Huh? When you are conducting experiments to determine whether, to discover a cause and effect relationship in science, which is the most powerful relationship, actually, cause and effect relationship, if you can obtain it, if you can establish it. Usually, experiments can be conducted to see whether there's a cause and effect relationship. If you are very lucky, if you have all the if the situation is suitable, you can conduct what we call a controlled experiment. This is the most powerful tool in science. The most powerful apparatus in science is the controlled experiment, where what you do is there is a stimulus, which is the cause, which you suppose is going to be the cause, and in this case it is the lighting. And you impose this stimulus to one group, and measure the output of that group. That's the effect, whatever it is. In this case, it is productivity. And then you also have another group, which is the control group, and you do not impose the stimulus to this group and measure their output and perform the outputs. Okay? If there's a difference, and of course, what happens is that you hold all the other variables should be held constant, should not change. So what is the place where all the other variables can be kept constant? What do we call this place? What is the name of the place where all the variables can be kept constant except one? It's laboratory. Okay? The definition of laboratory is exactly this. A laboratory is a place where we are able to control all the variables. So we hold all the variables constant. For example, we don't let the temperature to change when the pendulum is swinging. We don't let any air currents. We don't let the pressure to increase or decrease, etc., etc. We can control the lighting. So that's a laboratory. So if you are very, very fortunate and lucky, you can conduct such an experiment in the laboratory. Okay, take a 10-minute break and continue.